All right, today we're going to be taking a look at building a battery pack out of these really old laptop batteries. I've had these things laying around for about 3 years, and they kind of have a bit of an interesting story behind them, which I'll get into later. But these were pulled out of laptops. They have a manufacture date, most of them around mid-2014. So these are about 6.5 years old now. And as I said, they've been sitting around for the last 3.5 years, uncharged, untouched, and unmaintained entirely. So there's a good chance that a lot of these are going to have very low cell voltages, and we're going to have to do some recovery in order to get these back, if we can get them back at all. I've checked the output voltage of some of these, and I can't seem to get any voltage out of these connectors whatsoever. Of course, some of these, the wiring on the connector is completely ripped off, and I really don't know how these are in such bad shape, considering the fact that they're pulled directly out of laptops by me and just sat in a box since then. But anyway, these were pulled out of Acer C720 Chromebooks. They have a rating of 45 watt hours. And depending on which label you look at, they're either 3,990 milliamp hours or 3,920 milliamp hours. Not sure why that's different in two different parts. But these are a little bit interesting because they are lithium high voltage packs instead of the traditional lithium ion. Now, I don't really know what the chemical differences are between lithium ion and lithium high voltage. But the practical difference is a lithium high voltage cell, such as this one, which is pulled out on one of these packs, has a maximum charge voltage of 4.35 volts instead of 4.2 volts, which is interesting. And I want to do some testing on these batteries because of that. I've done videos in the past where I've compared using 3S or 4S lithium packs in order to replace a 12 volt system. The issue with using lithium battery packs to replace a 12 volt system is the fact that the voltage charge ranges just aren't the same. If you use 3 cells in series, you have too low of a voltage throughout basically the entire discharge curve. Or you can use a 4S pack, and that gives you too high of a voltage throughout the discharge curve. The only real way to get 12 volts is to use 4 cells of lithium iron phosphate batteries. Those are a little bit harder to come by, and you're not just going to pull those out of like a laptop or something like this. You're not just going to find a lithium iron phosphate battery. That's something you'd have to go out and buy new. These might be a little bit better. From my understanding, lithium high voltage batteries still have the same minimum voltage of about 3 volts per cell. Now, conveniently, these batteries even tell you the charging current and voltage that they need. So 1.7 amps at 13.05 volts. Which means that you have, well, these are 3 cells. You can see them and feel them in this battery pack. There's 3 cells, and I've also disassembled these, and I know that they're 3 cells. But anyway, that makes it 4.35 volts per cell. I'm not sure whether the charge current's only 1.7 amps. That's well below 1C rating because these are rated at 3,920 milliamp hours. I have taken these apart before, and I have a couple of cells out of one of these packs. I kind of saw these laying around in my pile of stuff, and I thought I should probably do something with them because they're just kind of sitting there going to waste. One of my battery packs was already partially disassembled, and I pulled 1 cell out of it and used it for a project. But there were still 2 cells sitting in it, so I wanted to test the capacities on them and see if it was even worth taking apart these 6 batteries to do anything with them. And these are those 2 cells. This cell was at about 3.5 volts, which is still a reasonable voltage for a lithium battery to be sitting at. This cell was at like 1.5 volts, so I had to really slowly bring this guy up to a reasonable charge voltage and then charge it off a normal charger. Anyway, the important thing about these 2 is that I did a discharge test on them. So I charged them all the way up to 4.35 volts. Then I discharged them at 2 amps down to 3.2 volts. And the one that had 3.5 volts per cell had 3,680 milliamp hours, and the one that was completely dead that I recovered actually had a bit more. It was 3,730 milliamp hours under the same test. So these are still testing well over 90% of the claimed figures on the battery pack label. So I do think it's definitely worth, I mean, if they all recover like that, obviously it's going to be worth saving these things. But anyhow, another interesting thing of note, there are 6 batteries here. They're all pulled out of the same model of computer, but one of them is a Sony battery, which is interesting. It still has like the same manufacture date, so apparently they use 2 different suppliers for the batteries. This one up here says Sony Electronics Co-Limited on it, and these ones don't really say anything about the battery manufacturer as far as I can tell. This one says Acer on it, but I don't think Acer makes their own battery pack. Having taken apart some of these batteries before, what I'm thinking I can do is just pop this cover off, or probably cut it open more realistically, because I believe it's glued or ultrasonic welded, one of the two. But I can pop this cover off and we can get access to the terminals to every cell that's in these here, because these do have a little, I don't know if it's technically a BMS or whatever, there's some kind of protection circuit in this cover that doesn't have like a lithium battery, so I can go stabbing this with a knife and not really have to worry about it too much. And I'm not intending on taking off any of the rest of this. I'm just going to leave it, and then we're just going to solder everything in parallel at the ends here, because we've got real nice tabbing wire that comes out, and we should be able to do everything without having to completely disassemble these. I'm just going to leave them in a 3S pack. It is going to be a little bit higher voltage than a normal 12 volt 3S system, so that'll be good for us. And one other thing I did note about these cells is that they have some kind of a protection device on them. All the current has to go through this little guy. I'm not entirely sure what it is. I initially thought it was a fuse. It's either some kind of regular fuse, a thermal fuse, or maybe some type of PTC. I'm not real sure what that is. Definitely some kind of protection because it's in series with the batteries, but it doesn't seem to have a whole lot of voltage drop across it when you pull current through it, so I'm not entirely sure what that little guy is. Anyway, we're going to use some brute force and see if we can't get these guys open. We'll check the cell voltages. I'll probably end up just cutting off this end once we get this open, because there's no point in having this extra thing for our purposes. Hard part's going to be getting in here, so I'm thinking we can kind of just pry it open, hopefully, and see what we get. I will note with batteries like this, you don't really want to go messing around with like metal tools and stuff, but I also know that all of the actual battery contacts are over in this area, so I think we're pretty safe cutting along this edge and not hurting anything too badly. Alright, there we go. Remove the little piece of plastic there. There are the 4 connections that I was talking about. Should be able to pull this board out of here. We should be able to cut those connections off the board, or peel them off the board. One thing I did find interesting about this guy is that the tabbing wire on the batteries it's not soldered to this board, it's spot welded to the circuit board, which I don't think I'm not sure if I've seen that before, but I haven't disassembled too many battery packs before either. There's a little temperature sensing thing. So that's our little charge board. Those are the battery terminals. So we'll grab a multimeter. That in there. Let's see what we got. Our entire pack voltage is 6 volts. So yeah, that's pretty bad. Apparently positive is on this side. So first cell is at 1.8 volts. Second cell is 1.9. So first cell is at 1.8. Second cell is at 1.9. And third cell is at 2.6. So that's definitely going to take some work to get that guy recovered. Oddly enough, this battery is also constructed in a different way compared to this one. If you see that, the little cover that looks like it's going to pop out is on the top of this one, and it was on the bottom of this one. Alright, so we're going to set this one off to the side, and we're going to go ahead and pry open another one, which should be effectively the same. This time I'm just going to attack this little cover that comes off, because these ones are a little bit more easy to see what's going on, I think, than that last one. So the last one, I think that was just on the bottom side, and for some reason this one's on the top. So these batteries, as I mentioned, do have a bit of a story behind them and how I acquired them. Back in high school, I took a class, or a series of classes, that was run by an organization called Project Lead the Way, or PLTW. Not sure if it's just a thing in America or if it's in other countries, but some high schools have it. And they have 3 different sort of tracks you can go down for your 4 years in high school. There's an engineering one, a computer science one, and a medical one. Now, I did the engineering path, and the final year of your engineering, or of the engineering path of Project Lead the Way, is effectively like senior design that you might do in college. So that last class, it kind of just walks you through the process of designing a product effectively. So you start out with brainstorming a bunch of different ideas and things. But anyway, the idea that we eventually settled on, because it was kind of a new concept at the time that hadn't really been implemented yet, was to do a 3-screen laptop effectively. So you had, like, at that time there was this thing called Project Valerie, which was a Razer product, and I don't think any of these things really took off. But our main idea, instead of doing a 3-screen laptop, because that would be, you know, a rip-off of that prototype product from Razer, we decided to do a laptop case that allows you to add 2 screens. And we pretty much messed around that entire class, and we eventually ended up throwing this thing together in the last 2 or 3 weeks of the class. And it was functional. It wasn't great, but it did work. We had a Acer C720 Chromebook in the middle, so we needed a total of 3 screens, which meant 2 more display outputs. And those Chromebooks had 1 HDMI port, so we had to add our own HDMI port. We did that through a USB adapter. USB 3.0 to HDMI, which is a reasonably common adapter, it seemed like. It was only like $10 or something. But it didn't support Linux, so we had to go through the whole process of installing Windows on one of those Chromebooks, which was wasn't actually that hard, but we had to buy a bigger SSD, because of course you can't install Windows on a 16 gigabyte SSD. And yeah, that was a big thing. But when we first started that project, we went down to high school's IT department, and we asked them if they had any old Chromebooks laying around that we could salvage parts from. And at that time, they were actually getting rid of the Acer C720 Chromebooks. The guy in charge of it was just like, here's this pile of basically e-waste. That was a bunch of old broken Chromebooks. He gave us one good Chromebook to use as like the base to actually use for testing and whatnot. But we told him we needed a couple of screens. He turned around, he had this big pile of screens, and just like grabbed a handful of them and gave it to us. There's probably like 8 screens in that pile. He didn't care at all, because, you know, they were getting rid of those Chromebooks and he had so many of them. Didn't matter. And he gave us probably like 10 or 12 scrap Chromebooks that were just useless to the school district, because they were broken and they were trying to get rid of that model of Chromebook anyway. So we got all of those. He didn't want any of the parts back, so we stripped all of those Chromebooks down for the batteries, and got the screens out of them and everything else. And he didn't want any of the parts back, so I just took the batteries home, and I figured I would do something with them eventually. And then, you know, I was planning on making a battery bank out of them. And I kind of forgot I had these, and well, I didn't forget I had them, I just never got around to doing anything with them. So yeah, today's project is kind of what I've been procrastinating for like 4 years or something, to get these guys back up in a running condition, or, you know, using these batteries for something besides paperweights. So anyway, needless to say, I didn't pay anything for these batteries. They were completely free, so I mean, if I can't do anything with them, it's not a huge loss. Okay, so we've got our pile of plastic covers and BMS boards, I assume. I don't know if these do balancing or if the computer itself does balancing, because this connector very clearly has multiple things going to it besides just power and ground. So anyway, this board does something, but we don't need that anymore. We're going to keep checking on all these and see what kind of cell voltages we have. That one's 2.1 looks like. That's pretty reasonable. Of course, one of them's at 2.1 and the very next one I check is at 0. Oh no, it's at 1.67. I guess I didn't poke through the oxide and the solder or something. That one's at 2.5. So that battery probably has a reasonable chance of recovery. Honestly, I think most of these have a reasonable chance of recovery. No idea how much capacity we're actually going to get out of them. That's going to be the hard part. 1.9 volts, 2.3, basically 2.0 looks like, yeah, 2.0. Yeah, 3.7, that one's, yeah, 3.7, this one's, yeah, 3.7. So this one is perfect. It's a little bit low for a storage charge, but this one is in great shape. We should just be able to charge that one up and test it. No problem whatsoever. And I don't think I've tested this one yet. 1.9, 1.9, 2.0. So not bad. Not great, not bad. And I should figure out which way is actually, or which one of these is the most negative terminal. So that's negative 6 volts. So ground is the top one then? Yes. So ground's the top one. So the way I'm going to recover these guys is by using one of these TP4056 charging boards. So these are designed to charge lithium ion batteries. Just takes USB in. It'll charge it up to 1 amp. But one nice thing about the TP4056 is that it has a recovery mode. So when you first hook this up, this little chip, of course, has to know what the battery voltage is. And if it realizes that the battery voltage is below 3 or 3.5 volts, it will not charge this at a very high rate until the battery voltage comes up above a safe level, which is exactly what I need this to do. So I have this plugged into one of those USB charger doctors, so I know how much current's flowing through this thing. And right now we have 120 milliamps going into the cell, which I think is fine for recovery. And as that voltage comes up on this pack, the battery, or the TP4056 will start putting 1 amp into it once it gets above a certain threshold. And what I'm going to do is just charge with the TP4056 until it starts to get to the point where it's putting in 1 amp, which shouldn't take very long. I have to keep an eye on the battery temperatures as all this happens. But anyhow, we should be able to recover probably all of these cells. The big question here is whether or not these cells stay balanced or if they have an even capacity across the pack. So we're going to have to do some testing on that in order to make sure that they're okay to be left in series like this, or if I'm going to have to disassemble all these packs and try to capacity match the cells, which would be a real pain, but we could do it if we had to. The main part of the reason why I like these is that they're pre-wired. We don't have to do anything but slap the connections at the ends together and probably cut off this extra piece of plastic because we don't need that anymore. So since one of these batteries is already at a reasonable charge level, what I'm going to do is take one of my balance leads, we'll cut off one end of it, stick that onto our charge, or the tabs on the battery, and we'll just try to charge this thing up, see what happens. It should charge just fine. I don't see any reason why it won't. So I am just soldering this balance lead on here for testing purposes for now. I'm not going to be leaving this on here. It's just the easiest way to hook this up, really, is just to solder it straight to these tabs. So I've been using this little dude to charge these batteries up so far. That's what I've done with our single cells. And the reason why I'm using this specifically is because it is the only charger that I have that can properly charge lithium high voltage batteries. And I am going to try something new here. I haven't done this yet, but I'm going to attempt to charge or power the charger off of this little 12 volt lead acid battery. Now the reason why I'm going to power this off of a 12 volt lead acid battery is because this charger has a discharge function that will allow you to take power out of your battery that you have hooked up to your outputs, in this case it'd be this lithium guy, and push it back through the output into the power supply. And the reason why you do that over just the internal discharge is because you can only discharge at like 12 watts, I think. It's a pretty pathetically slow discharge if you're not discharging back into something. So discharging back into something will just give me a little bit more power. And of course we have to discharge it in order to be able to recharge it. So anyhow, theoretically, we should be able to plug this in here and we should be able to read all of our cell voltages, which are actually super well balanced. Every single one of these cells says 3.737 volts. So that is pretty much perfect. I am also going to need a connector to clip onto these guys. Okay, so we're going to use these alligator clip wires, hopefully, to connect these guys. And these are kind of terrible alligator clip wires. They have 10 gauge wire in them, so voltage drop isn't much of an issue, but they're not like 10 gauge silicone wire. It's 10 gauge wire that's coated in oil and gasoline resistant plastic, so they are super stiff. Alright, so there we go. That's 11.2 volts there. I should be able to charge this thing. You'll auto cell detect. We're going to go charge mode. In voltage 4.35, that'll be per cell, and then charge current 1.7 amps, which is exactly what the sticker on the battery pack says you should use. So that's what we're going to do. We're going to say start, and say charge to 13.05 volts, which is exactly what we want it to do. And there we go. Now here in a couple seconds, this charger should spit out. This is already kind of, this is looking worse already, because when I first plugged this in, I said that the cells were incredibly well balanced. Well, as soon as we started charging it, the balance it hasn't actually gone that far off. For 3.9, 3.91, and 3.95, so one of these cells is a little higher. But what I'm curious about, okay, so this is the internal resistance of every cell. So we have an internal resistance of 61 milliohms, 65 milliohms, and 95 milliohms. So that internal resistance is really high. I don't know if that's normal for a laptop battery or not. Maybe that's just kind of par for the course on a battery like this. But for like the RC batteries that I'm used to charging off these things, you get internal resistances of like 10 milliohms at most. So we're going to charge this thing up, and then we're going to discharge it. We're going to see what happens. I'm not entirely sure how well it's going to work for us, but we're gonna try it, see what happens. Alright, so I did go ahead and go through and individually test every one of these packs, and I have also created a parallel array of all 6 packs. The lowest number of amp hours that I got out of any single pack was 3.42. And that's 3.42 amp hours out of 3.92. So that gives us a capacity of 87% of the factory rating on the worst cell, or the worst pack, I should say. The best pack had a capacity of 3.7 amp hours. So the worst pack was 3.42, the best pack was 3.7 amp hours, and most of them averaged out to be around 3.5. So really, these batteries are in decent shape considering the fact that they're 6 years old. And to go into a little bit more detail about it, the center pack, the center cell on all of these packs, cell number 2, was the best cell on every single one of these packs, and then number 1 would follow it, and then number 3 was the worst. I'm not entirely sure why they're like that. Maybe cell number 3 was closer to a heat generating component or charge circuitry or something, or maybe cell number 3 got less attention from the BMS board, or maybe the BMS or whatever those little charge boards actually are, these little protection things that we pulled out earlier. Maybe these cells were powered off of that, or the board was powered off of these cells, I mean. I'm not really sure why cell number 3 was always the worst, but it was. Anyway, we can take a look at this kind of horrendous soldering job on the back of here. So As I mentioned, we had 5 batteries that were kind of unbranded, and then we had one Sony branded pack. The Sony branded pack is here on the bottom, and you can see that the tabs don't line up perfectly. So most of these I just managed to bend the tab over, solder it down, bend the next tab over, solder it down all the way down the line. But of course these didn't line up perfectly, so I had to put little jumper wires in here. That's not too big of a deal. So the next thing is going to be to rework the wiring a little bit so I can get this into the case, slide it down in there. I'm not going to do what I did with the last battery pack and kind of wire in my own protection circuitry and all that and try to make it look pretty. I'm basically just going to turn this thing into a kind of just like an RC car battery where you've got the balance lead hanging out of it and you've got the power lead. And that's all I'm going to do to this thing. And I think for now, at least, that'll work just fine for my purposes. The only other thing I'm going to do is cut off these little mounting points on the side here because we don't need those, and then that'll sit nice and flat at the bottom of this case. So anyway, I'll go ahead and fire up the soldering iron, move this around, and then we'll do some more capacity testing on this thing. Alright, so I've done a couple of capacity tests, and I have found this battery to be somewhere in the region of 20 amp hours, about 225 watt hours. So I was estimating this pack to be somewhere in the range of 21 amp hours, and I'm going to go ahead and label it as a 20 amp hour pack. But anyway, I did 2 different discharge tests. One was at approximately 0.2 C or 4 amps. And that got me 21.3 amp hours and 241 watt hours. And then I did another discharge test at 10 amps, which is about half of a C for this pack. And that got me 20.3 amp hours or 222 watt hours, which is a pretty decent result for a 6-year-old used battery pack. So in order to do the capacity testing, I was just running a 12-volt inverter off the output of this pack, and I had one of these power meters in series with it in order to measure the watt hours, amp hours, and of course voltage and current as I was discharging the pack. Now, I almost always use this particular 300 watt ExoVision inverter to do testing of lithium batteries because it has a fairly low cutout voltage for a 12-volt inverter. In fact, it doesn't even start beeping and complaining about low voltage till I get down under 10.5 volts, which is usually when I stop the test. So I've gone over this in other videos, but really, once you're underneath about 3.5 volts per cell on a lithium battery, it's fairly low by that point. Now, one cool thing about this pack is that it is capable of being charged all the way to 13.05 volts, which is pretty close to what you'd expect a voltage of a fully charged lead-acid battery to be. So what I've noticed from my testing is that this thing does hold its voltage a bit higher than a traditional max 12.6 volt lithium-ion battery pack, which does make it work better for a 12-volt system. Now, the recommended charge rate for the individual packs in here is 1.7 amps, and we have 6 of them in parallel, which makes our charge rating, I think, 10.2 amps. And charging at 10.2 amps, the cells don't get warm at all. But discharging them at about 10 amps, the cells were getting ever so slightly warm. Definitely not a concern at all. But discharging them at 20 amps, they definitely started getting hot. So this is not a high discharge rate pack by any means. It's something that you could use to power lighting or something like that. Though discharging a pack like this, it was around 11.5 volts for most of the discharge cycle, so you're getting 115 watts or so out of this at 10 amps, which is a pretty respectable amount of power, really, and it can sustain that for a couple of hours. And another thing about only running these down to approximately 3.5 volts per cell or so is that the cells stayed fairly well balanced with each other. So when I did the 4 amp discharge test, my highest cell voltage was 3.584 and my lowest cell voltage was 3.558. So less than 20 millivolts of difference between the cells. And when I'm listing those voltage, I'm listing the open circuit voltage for those. But what that tells us is that the capacity of each parallel group of cells is pretty similar. Unfortunately, the internal resistance of the pack that's on cell 3 is a little bit higher. That doesn't really matter too much. It just means that those cells sag down in voltage a little bit more than the rest of them do. And it also theoretically means that they should generate a little bit more heat than the rest of the cells, but that doesn't seem to, I couldn't feel a difference between cell 3 and the rest of them. So in a future video, I will probably get this thing out again and take a look at the discharge curve that this thing gives. I didn't actually plot the discharge curve when I was doing my testing for this. I just did the simple way of getting the amp hours off of one of these little meters. But getting the actual discharge curve for this would be interesting to compare it to what I would expect out of a lead acid system in terms of the voltages that this can maintain. But anyway, this is pretty successful. It turned out nice, minus the little bit of glue that I let drip out. But anyway, I think this turned out pretty well, and I'll probably get some good use out of it. So if you like that video, go ahead and drop a like down below. If you have any questions or comments or concerns or whatever else, go ahead and leave that down below as well. And if you want to see me do more testing on this or work with other things similar to this on this channel, go ahead and click on that subscribe button. That's it for this video, guys. See you in the next one. Bye.